Hey, well, we're back in the Simkins Physics Corner today with a little combination circuit. We've been working on series and parallel circuits, but what happens when you put the two of them together? So I wanted to show you a little example of some strategies we can use to break complicated circuits down into less complicated, more simple circuits. So we take a look at this guy, we see what's going on. We have a series part we can consider anytime there's one path. There's not really anything interesting going on there. As soon as we hit this, we have a branch where we branch off two different directions, and by definition that's called a parallel circuit. It makes sense because you could think of these as two parallel lines. In fact, they are. And so these two are in parallel, and they come back together, and then they split off. We have a second parallel segment, and it comes back to our battery, to our supply of voltage. So what do we do with this? Well, every time we see a parallel in a combination type of setup here, we want to get rid of those parallels. And by get rid of them, I mean we want to combine them together to see what is the net effect. We know that when we have any resistors in parallel, the sum or equivalent resistance of those two resistors is always going to be less than the smallest resistor. So we know it's going to be less than 100 if we combine these two together in parallel. How do we know that, or what equation do we use? Well, if we look on our AP Physics equation sheet, it's written as sigma r pi is equal to 1 over r I, which is kind of a weird thing, but if you understand what the summation symbol means, it's pretty straightforward. Let me zoom in a little bit. It looks really tiny. Okay, there we go. And so basically what comes, oh, I forgot something very important. Thanks, before you comment and thumbs down the video. There you go. Get the correct equation there for you. All right, let me scoot this up just a hair. So here we are. We want to find out the equivalent resistance for this segment. So what we would do is you say 1 over Rp, meaning the equivalent resistance in parallel for a certain segment, is 1 over 100 plus 1 over 250. Oh, 250. 1 over 250. Sure, you know what I'm talking about. Now, when you type, you can do this in your calculator as a fraction if you want to. Just be careful with your parentheses. But don't forget the crucial step. Notice that we're not solving for Rp. We're solving for 1 over Rp. So whatever answer you get, like in this case, I've done 1 over 100 plus 1 over 250. I have to do 1 divided by that answer to actually get Rp. So in this case, our equivalent resistance for that segment would be 71.4. I'm just going to write that in the middle here to remember that this segment of my circuit is giving me 71.4 ohms. I do something similar down here, so 1 over Rp for this little parallel arrangement would be 1 over 350 plus 1 over 200. Okay, so again, we do 1 over 350 plus parentheses. Be careful with those guys. And that's not the answer. That's really small. We have to do 1 divided by that in order to solve for Rp. So Rp of that segment is 127.3, we'll round it to. So I'll just write that over here, 127.3. All right, so what do we do from here? Well, if you imagine this whole chunk of stuff is giving us 71.4 ohms of resistance. This whole chunk of stuff is giving us 127.3 ohms of resistance. And so we can think of it as chunk number 1 and chunk number 2. If I redraw it quickly here, I often do this when I'm combining circuits together. Now, keep in mind, this isn't exactly the same circuit, but it's representing what we have going on as a net effect, if you will. No problem. We have 71.4 and 127.3. Now, this, by definition, since there's only a single path to follow for our electrons, is a series circuit. And the nice thing about series circuits is the equivalent resistance is just R1 plus R2 in this case. All right, so for the resistance here, all we have to do is algebraically add those two together. Nothing crazy, no fractions in this case, and we get 198.7 ohms. What did we just figure out? We just figured out that this segment gives us 71.4 effectively. This segment gives us 127.3 ohms effectively, and that means overall for our entire circuit, when we add those together, we can say for certain that our resistance of the entire circuit is 198.7 ohms, and our total voltage for the circuit is 24 volts. Why did we just do that? Because we want to find out the current, right? The total current, which is often a strategy we use. We want to know what's the current over here. Now, by Ohm's law, V equals IR. Okay, V equals IR, or we can rewrite it as I equals V over R. Anytime you have a complicated circuit, figure out the total current, and then we can start to hash out the details along the way once we know that total current. So here we go, 24 volts over 198.7 ohms. Looks like our current at the battery, or I call it the total current, is And we're back in action, and you may notice I'm dressed differently. I made an error in the last video, but I want to bring you the best, so I'm fixing it here real quick for you. I don't know what happened. I just typed in the calculator wrong for the current, and so the current here would be 0.12 amps. All right, now what do we have so far? Well, we know that the total current at the battery at the beginning of the circuit is 0.12, I'll make it real precise, 121 amps. And we know in series, at any point along a series circuit, this single loop here, the current will be the same. So that means dumping into this branch, we'll call this branch A here, dumping into this branch, we have 0.121 amps of current coming into there. All right, and so now it gets a little tricky, right? Because you're thinking, okay, I know there's current coming in here, and by Kirchhoff's junction rule, the current will be split, not necessarily evenly, in fact, not evenly, because the resistors are not the same. So what do we do from here? Well, we know if we take these parallels and smash them together, combine them, we had this picture, right? And in this picture, this is a simple series circuit. Oh, what do we know about series circuits? The current's the same everywhere. So what that tells us is that the current coming in to this, we'll call it branch A, is 0.121 amps. What does that help us with? Well, we know that the resistance of branch A is 71.4 ohms, and we know the current coming into branch A is 0.121 amps, and so we can just multiply these two together. Let's see if I can do it right this time. Times 71.4, and that will get us 8.64 volts. 8.64 volts what? Oh, 8.64 volts is being dropped in this branch, which means between this point and this point, we have 8.6 volts. Now there's 8.6 volts between these two places, these potential difference between these 2 points. Since it's parallel, and in parallel, all of the branches get all of the volts, these guys will both, V equals 8.6, they'll both get all of those volts, 64, call it. And this guy will get V equals 8.64 volts. Okay. Now if I haven't asked you what are we actually solving for yet, you really can solve for anything. I'm just showing you the generalized strategy for how you can break circuits into pieces. So just for fun, let's say that the problem we're asking us to calculate what is the power consumed by resistor 2, right? Just to make things interesting. Well, here we could see that resistor 2 has a resistance of 250 ohms, and we've now determined that it receives a voltage of 8.64 volts. And so with R and V, of course, you should think of V equals IR, we can get I, V over R. Now we can find the current going through resistor 2. So let's go ahead and do that. 250 over, I'm sorry, let's not make calculator mistakes again. 8.64 divided by 250 is 0.03, rounded to 5 amps here. That's the current going through resistor 2. And then, of course, the problem said find the power consumed by resistor 2. Power is current times voltage, I times V. And you can go ahead and just drop your numbers in there. Times our volts, which is 8.64 volts. And that would get us our final answer here, 0.035 times 8.64. That would get us 0.3024, and it would be watts because the problem is asking us for how much power is consumed. So I'll give you a snapshot of the work. I'll move my face out of the way here for our recap. And you can see that the general strategy is applied. First, get the parallels, equivalent resistance. So any parallel segment of a circuit that you see, get the equivalent resistance for that segment. Then redraw your circuit as a simple series like this. Use the total resistance and the total volts to find the total current. And once you know the total current coming into your first branch, you can use the equivalent resistance of that part of the branch, like we did here, and the current coming into that branch, like we did here, to figure out the voltage that drops across that branch. That will get us into here, and of course, we can figure out the volts that each of these guys gets, because if we look at this picture, by Kirchhoff's loop rule, if this top segment of the circuit is using up 8.64 volts, and we started with 24, that means that the bottom segment there will be getting 15.36 volts down here. So if you wanted to jump in and find the power of resistor 3, you could do it like that. All right. So don't forget to like and subscribe. Have a great day at doing some physics. Share with your AP Physics friends. Let me know if you have any questions. Just leave it in the comments, and I'll do my best to help you out. Have a good one.